So welcome everyone to the 5th episode of the Machine Learning Seminar at Helmholtz-Zentrum Gestacht. Today we are covering a really interesting paper which uses generative adversarial networks to generate cloud reflectance patterns on a large-scale data set. We're going to talk about this paper, what they're trying to do, why they're trying to do it, and go through this myriad of different machine learning tricks they use, which really goes right up to the bleeding edge of what's possible with these frameworks today. So we will discuss this GAN framework. We'll give a bit of background on it, and then we'll look at all the different variations and all these essential tweaks that are required to actually get good results out of it. So what are they trying to do here? Essentially, they want to generate pictures of clouds, these reflectance images of clouds, like this, from a bunch of meteorological variables like wind speed, temperature, a few others. And so given all this input data around the globe, they want to generate the region of the globe seen by a satellite. So they want to generate 3 color channel outputs, essentially red, green, and blue, from about, I think, 20 odd or 24 odd input channels. Okay, describe that in the introduction, right? 44 input channels, 256 by 256 pixels, and the output is going to be 3 output channels, red, green, blue, or rather infrared, yellow and green is maybe more accurate. And for this same 256 by 256 image. So we've seen a few of these prediction frameworks before. We covered one last week that was probabilistic, but it gave kind of a range of possible outcomes for each individual pixel of the output. What these guys are really trying to do is come up with an output which is coherent, where all the pixels make sense together, and it actually looks like an image of cloud cover like you'd capture from a satellite. So why would they want to do this? One really good reason is, so in these climate models, it's important when computing the Earth's energy balance to take these clouds into account. So you have radiation coming in, generally shorter wave, and then going out, generally longer wave. And the cloud cover, especially in the tropics, really contributes a lot to this energy balance. But to actually model this using physical models requires information at very fine spatial scales, which is really difficult to compute over the whole Earth. So a number of approaches use these parameterizations where we say, given other variables which we can compute at coarser scales, like overall humidity, temperature, wind speed, and so on, we try to guess the effective cloud cover and how much radiation this will reflect. So there are different kind of approximate heuristic schemes for doing this, but this is maybe, to the extent that it's going to work and produce realistic outputs, a more principled approach in that given all these meteorological variables, these inputs, they're going to guess, based on these variables spread across the entire globe, they're going to guess what does the cloud cover look like at each point. And then this could be used to calculate a radiative balance in one of these models. Maybe if any of the people with more of a background in earth science want to chime in here, talk about this idea, the pitfalls, the ways this might or might not be used, this is a good time to do so. Then I'll jump into the actual data itself a little.
Maybe we discuss this later. I mean, I think it would be great just to go through and then we could jump in.
All right, well, sounds good. So I'll just quickly talk about the data. I just had to have a look because, and maybe this is just a clarification for me, I'm not totally sure what the reflectance data means. I don't know how it's related exactly to the intensity, the illumination values that are recorded by the sensors on the satellite. I looked it up on the website, This is actually the data streaming in from today, which I updated about an hour ago, because I guess in a few more hours they're going to take a picture of us in Hamburg as well. And you can see it streaming in. There's a few gaps. I mean, you can choose on this website, on NASA's website, the time, location, and all these various image channels. Like a lot of these Earth science data products, it doesn't only give you the raw data, but also it computes a lot of things from these models, like the fraction of different ice crystals based on these observations in clouds, the amount of chlorophyll in the ocean at various points. So there's really a lot of information you can get from this NASA website. But beyond that, I'm a little hard-pressed to say what exactly these three outputs mean, the reflectance, whether it's something directly measured by the satellite or computed using some kind of model. I don't know if anyone wants to clarify that, or we can get back to it later in the general discussion. There's a paper kind of about this whole data set as well, with a lot of authors. Okay. So, like I said, this approach that we're covering today, they want to generate, given these meteorological variables across the globe, they want to generate these realistic images of clouds as seen by the satellite. And they don't only want to calculate the kind of the expected mean value of the image given the inputs. They want to calculate actually sharp, realistic possible outcomes. And ideally, they'd like to be able to give you multiple possible outcomes consistent with the data, right? So given our meteorological values, we'd like to be able to produce samples from the probability distribution, essentially saying what are the plausible configurations of cloud cover given the meteorological values, which I believe they get from one of the ERA data sets, the meteorological values. So one way to do this is with the GAN framework. So this is kind of a diagram showing the overall structure of the two networks, not one, but two neural networks that are used in a generative adversarial network approach. So there's two networks are called the generator and the discriminator. The generator is what they're using to make these fake cloud images consistent with the meteorological values and trained using the real images. So in training, you have access to a real image of clouds taken by the satellite as well as the meteorological values, and you want to essentially train this approach to predict the cloud image conditioned on the meteorological values. So the generator network, in a classical GAN, it takes a bunch of noise as inputs. It transforms the noise as activity is streaming through the successive layers of a neural network. And it produces a fake sample, in this case, an image of clouds, conditioned on the meteorological variables. Then we also have real samples from our data set, so actual cloud cover. So we have actual cloud cover images and generated fake cloud cover images from our generator network. Now, both of these are fed into a discriminator network. This is a neural network which takes as input either the real cloud cover images or the fake images generated by the generator network, and it has to tell the difference. So it should say, for example, output 1 when the data are real and a 0 when it's fake. So these two networks are sort of in competition with each other. The generator is trained to fool the discriminator, and the discriminator is trained to tell apart the generator and his fake samples from the real samples in the data set. And that's because they're adversaries in this task. This is where the name generative adversarial network comes from. So this is from a blog post. We're linking it in the description and in the email. But I'll just briefly mention the original paper. This is Goodfellow et al. which introduced this concept from Yoshio Benjo's lab. I believe Yoshio Benjo's lab is also where the current paper came from, in Montreal. Yeah. So they introduced this framework, as we see in this diagram, of these two networks in competition, one counterfeiting the data and the other telling the real from the fake data. And the only thing I want to discuss from this paper is this equation. And it's a little daunting, there's a lot going on, but I want to go through it bit by bit for a couple minutes and just explain what this means and how this relates to this adversarial game that the discriminator and the generator are playing with. So D is discriminator, and when we say D here, we mean essentially we're taking a maximum over all possible values of D, right? What we mean is all the weights and biases, all the free parameters of the discriminator network, which takes input images and tells you, are they real or fake? Are they real images taken by the satellite, or are they fakes created by the generator network? So basically for the discriminator, we're trying to maximize all this function, right? So the first term, which only depends on the discriminator, not on the generator. So we're saying if X is taken from the distribution of our data, that is, if X is a real sample, if X is a real image of clouds, I want to maximize log of D of X, right? So basically you can think of D, the output in this case, as essentially the probability that the sample is real, as estimated by the discriminator network. So the discriminator network sees an image of clouds. It knows either it's a real image taken by a satellite or a fake image created by the generator. And we're trying to choose the discriminator to maximize the probability of assigning the real label to real data. Okay, that's the first term. Basically, if we put it into words, we say the discriminator network should correctly identify real data. It should assign a probability close to 1 for real data being real. Okay, now what's the second term? This is an average not over real data, but over, so we have the noise Z going into the generator, and then we put that through the generator and we get an output. So G of Z is actually a fake data point. Yeah, so what this term here says is if we have a fake data point generated by the generator, right? So the generator looks at the meteorological values and outputs its fake image of clouds, right? Then it's trying to fool the discriminator. So it wants the discriminator to assign a large score to this, but the discriminator wants to just assign a small score. So this is why we're trying to minimize this term with respect to G and maximize it with respect to D. So for the discriminator, it's trying to maximize this log, which means maximize what's inside, which is minimize this term. So basically the discriminator wants this term to go to 0. Then for the generator, we want the exact opposite. We want the discriminator to be fooled. So this first term says the discriminator should correctly identify real data. And this second term says that, well, we train the discriminator to reject fake data and maximize this term. We train the generator to fool the discriminator and minimize this term. So this is the whole framework essentially. And we have these two neural networks. G takes noise as an input. In our case, it will also take the meteorological values. There was no other conditioning information in this original paper by Goodfellow. And then the discriminator will take, and it will output an image, in our case of clouds. And then the discriminator will take an image of clouds either from the data or created by the generator. It doesn't know which. And it will also take the conditioning information, in this case, the meteorological variables. Yeah, so I think, this has been pointed out in the chat as well. I'm kind of skipping over the conditional versus non-conditional aspect, but the point is, if we're just trying to learn a distribution, then we have this framework here. If we want it conditioned on something else, like the meteorological values, then we have to feed that something else into both the generator and the discriminator as an extra input. Okay, so this is a basic GAN framework. For those who are interested, there's this really extensive tutorial that Ian Goodfellow published on GANs. This is some 60 pages, and you can really go into a lot of detail with it. So if you're interested in the details of GANs, this is what was known up till 2016. I think there's even a lot more known now. And I think maybe some people here also can give their own, perspective or feedback. But I think the general feeling on GANs in the machine learning community is that they're really good at a lot of tasks, and they're also notoriously difficult to get to work. They have a lot of failure modes. They can be difficult to train. Training two neural networks at the same time to do kind of opposite things is tricky. So there's quite a lot of literature on how to get them to work. And so if you're going to use them, you really want to dig into this. Okay, so that's the basic idea. I think going back to our original paper, and please, anyone just chime in, raise your hand, or write in the chat if you have any questions, if you want to stop and ask something. But going back to the original paper, okay, with this framework in mind, we can see what they do. They took the meteorological variables, and if we want to jump and see what those are, I believe they're in the appendix. There are things like, horizontal. There are latitude and longitude aligned wind components in atmospheric levels, temperature, relative humidity, scattering angle. I looked this up a little bit. I'm a little unclear what this is. Maybe someone can clear this up. Surface temperature is obvious, and latitude and longitude are just fed in as additional inputs because the image is not, so the latitude and longitude on the image are not stationary with respect to the satellite. The satellite is moving around the Earth, and so the latitude and longitude are going to change over time, as we saw in our little preview of today's data. Okay, so this is what the network is getting, and it's producing outputs like this. So in this image, we can in this figure, we can see, given the meteorological variables, on the left we have what was generated by our generator network, and on the right we can see the actual picture of clouds, which were collected at the same time as these meteorological variables were pulled from the reanalysis product. That is a fusion of model and observations. So, and there's a lot. Let me even zoom in a little bit more. There's a lot to say here. It's got these shapes of clouds really nicely. It's got the textures really nicely, although not always the exact match to the data. It really does look like a picture of clouds. And it looks like the errors, at least visually, at least to me, it's very appealing that these are kind of the errors or uncertainties you would make given what you can and cannot figure out from these meteorological variables, right? So maybe it'll tell you there's clouds, but not exactly how dense they are, not exactly the precise pattern of them. So this could be, this to me is a lot nicer than just getting some kind of blurry, kind of average output that you'd expect from a least squares fitting method. Okay, the other thing, of course, we can do, because these are generated by noise, although exactly what kind of noise we'll get to in a second, because it's not the same here as in the classical GAN, but because there's random variability fed into the network, and then an image coming out, for the same inputs, the same meteorological variables, you can do multiple realizations. So you can actually get multiple possible scenarios of the cloud cover for the same meteorological variables. And this is really interesting. It allows you to have uncertainty. It allows you to get a range of outputs to look at extremes. And again, we can see real differences, especially in the fine scale features of what these cloud patterns were. So these are 3 different possible outputs from the network for the same meteorological variable inputs. Okay, so these are the results I get. I think what we want to do now essentially is take a sort of a detour into what are the techniques they used to get this to work. How did they build their generator? How did they build their discriminator? And how did they change things up from this, this loss function, this framework, this minimum maximum 2-player adversarial game introduced in the original GAN paper to get good results on their problem, because they didn't just use it out of the box. So we go through this bit by bit. The first thing is something we've seen before, which is the UNet. We saw this in episode 2 when we were talking about machine learning methods that work on spherical data. The idea being that you start off with a few channels at reasonably high resolution. This is from Rinneberg et al. 2018 or 16 that they cite for the UNet paper, and the numbers aren't the same, but the idea is the same. So you might start with an image of a given size. Say here it's 572 by 572 with 1 channel, a grayscale image. Then we do some operations, some convolutional filters, and we go up to 64 channels while reducing the size of the image due to these edge effects of the convolution. So we lose 1 pixel on each side. Then we drop the resolution by a factor of 2 and increase the number of channels from 64 to 128. We repeat this after some more, we process a little more at this resolution. Then we drop the resolution again, increase to 256 channels. And we keep up with this pattern, right? As we go deeper and deeper into the network, the number of channels increases, but the spatial resolution decreases. So we're extracting more and more summary features that describe what's going on in each local neighborhood of the image. Then eventually we get to the bottom. In this case, we still have 32 by 32 images. In some cases, we might go down to a single pixel with many, many channels. And then we start going back up. We increase resolution and decrease the number of channels until we get back to the original image size or something very much like it. In this case, 388 by 388. In addition, we have these skip connections, these gray arrows, which is to say, when we go back up the right side of the U, decrease the number of channels, increase the spatial resolution, we're also looking back across at the information at that same spatial resolution or a similar spatial resolution. We're taking kind of the center of the image as in these dotted lines. So essentially, we are taking the information at each spatial resolution and recombining it back into the workflow as we go back up. And at the end, we have an image where every pixel of the output depends on every pixel of the input, or close to it. And yet, unlike, say, an encoder-decoder framework, where all the information has to pass through a bottleneck down here at low resolution, we're able to make the outputs appropriate to the local high-resolution spatial features by using the skip connection. So this is a basic idea of the UNet. As I said, we saw it in episode 2 for spherical data, and we are seeing it now for just general rectangular data. So this is something that they used in order to build their generator networks.
David?
Yeah.
If I may quickly interrupt, if you have the Isola paper open,
Yeah.
Isola, just because you explained the benefits of the UNet on page 1129, I think this is the it's figure 4. You can beautifully see the effects of the skip connections on the fine details.
I think we're dealing with maybe different versions of this manuscript, but maybe figure 5.
Figure 5,
Yeah,
exactly.
great. Yeah, exactly. So here they're performing a different task. They're saying if we start off with, well, they're translating one kind of image to another kind of image as we are in the Schmidt et al. In the cloud cover paper. I believe they're translating these kind of labels here. So category labels for different elements of the scene, a car, a person, and so on. And then they're trying to guess the image or several images which would be compatible with those category labels. And yeah, so what we're seeing here is with the skip connections, we're able to resolve much more fine spatial information compared to if we just force all the information through this low dimensional representation. So this UNet architecture really helps when you want to translate an image into another image. Okay. So yeah, we'll get back to Isola et al. In a second, I think. In fact, I think we can move on to it right now. So if we go back to the original definition of the GANs, right, in Goodfellow, we say we only have, we've got two main things going on. As we said, the discriminator should identify real data. It tries to reject fake data, and the generator tries to fool it into accepting the fake data. Now, this can be done anytime you have samples from a distribution, so our data samples. We could do it conditionally as well. We feed some additional conditioning information y into both the generator and the discriminator. They mention this in the original paper, but they don't do it too much. And that y in our case is the meteorological variables. Okay. Well, they do something else in Isola et al., which gets used, I think, quite critically in Schmidt et al. To produce these cloud images. They don't only try to fool the generator conditioned on the data, on the meteorological values. They don't only try to fool the discriminator when they generate an image. They also try to match the true cloud image that was taken at the same time as this meteorological variable. So it's not only this GAN framework, they're also adding a term to their loss which corresponds to simple supervised learning, right? So we have our conditional GAN term right here. We're saying we want to have we want to identify real data, and we want to reject fake data, and then the generator wants to get fake data accepted. But they add this additional term, which just says the generator, in addition to fooling the discriminator, should also just produce something like what we know to be the true cloud reflectance pattern that was measured by the satellite at the same time these meteorological variables were measured. And so what's going on here? We seem to be mixing two very different frameworks. On the one hand, we have the GAN framework, where we want the generator to fool the discriminator. On the other hand, we have this basically a supervised loss, where we just want the observed cloud pattern and the generated one to match. So why are we even bothering with the GAN? Why don't we just only use the L1, this loss? And what is this loss? Is to call it L1. This is basically just the sum of the absolute values of the differences, as opposed to least squared. They find it gives less blurry results. So why don't they only do this? Why not just train it to do the prediction? And the reason for that is that if you only use the L1, here we can see some of these results. You tend to get very blurry results. So if you only use the L2, you're only really encouraging the generator to get the mean answer right. If you're using the L1, it's more like the median. But in both of these cases, the loss is very simplistic, and it basically treats each pixel independently. It says the sum of square errors or the sum of absolute errors. Both of these don't take into account the fact that for an image to look like cloud cover, or as we see here, a car parked in a street or the side of an apartment building, it's not only the individual pixel values that matter, it's the combined set of pixel values. It's that they should make a coherent whole that looks like a cloud or looks like a car. And for this, these L1 and L2 losses aren't sufficient. So, but the discriminator can take this information into account, right? The discriminator will look at multiple pixels together, and if the image is blurry, the discriminator will say, oh, this is a blurry image, I'm going to reject it, because the true images of cars or clouds or what have you are not blurry. So in order to fool the discriminator, the GAN generator must produce sharp, non-blurry images. So this is why we combine these. This is why we absolutely need these GAN terms. So why not only use the GAN terms? Well, the GAN terms are pretty good at producing these sharp features, but as Isola et al. Point out, they're not so good at global low spatial frequency features, so large parts of the image. I believe they have some results where they only show, where they only use the GAN without the L1 term. And yeah, you can see it sort of works, but it resembles the original image less, and you get all kinds of weird hallucinated artifacts, like these discolorations on the side of the building, these weird stripes. Basically, the GAN is too free to produce just about anything, whereas adding the L1 term, the sum of absolute value errors, like we're just doing supervised learning, it kind of creates an output which is more tightly clamped to the target. So we're kind of combining the flexibility and the sharp features of the GAN loss with the kind of the overall accuracy of supervised learning. So this is what they take from Isola et al. Isola et al., I'll point out, also has code online. It's really easy to download and use. It's a very cool thing where you can train it to translate one kind of image to another. You put in a picture of day, you get night. You put in a sketch of a handbag, you get an output which is looks like a photo of one. It'll colorize images. It'll make pictures of buildings or cats or what have you from these segmentations. It translates satellite imagery into maps. It's a really impressive piece of software. And the code is online and it's in PyTorch. Okay. So another ingredient that they use, they list them here, all their tricks, and there really are a lot of tricks. Another ingredient they use is a multi-scale discriminator, which is proposed by Wang et al. Let me open this up. And the idea of the multi-scale discriminator is, instead of just feeding in the full image, either the real cloud image or the fake one made by the generator, they're going to feed in multiple different versions of it at different resolutions. So their goal in this paper, Wang et al., one of the co-authors, in fact, is the same as Isola et al. They're trying to generate really much larger, higher resolution images than people had done with GANs before. And they found that just feeding them directly at high resolution into the discriminator was difficult to train and difficult to get good results and a bit unstable during training. You just had to use so many parameters on these large images that you just couldn't get good training results in a reasonable amount of time from a reasonable amount of data. So what they did instead is they use multiple discriminators that work on different resolutions of the input. So you have a low resolution version, which So this, by the way, here is actually this beautiful image generated by their GAN, 2048 by 1024 pixels. And again, starting from this, pixel by pixel labeling of the different objects, they come up with cars, they get the different cars, different colors. They really synthesize a very coherent, believable scene here. So they have these multiple resolutions that they feed in. One of them goes through a discriminator that takes low resolution inputs over the entire image, and it looks at the lower spatial frequencies, the global features. Other discriminators will take higher resolution inputs, but process them in a way that only local information is taken into account. So they won't be able to detect whether the global statistics, the global features are correct. For example, the road kind of goes in a straight line and doesn't turn to the sky, that the white lines go in a reasonable pattern for traffic, things that you couldn't get from looking at only a small spatial patch of the image. That the shadows are in the same direction in different parts, which actually the shadows are pretty consistent across this image. These are global information. And then you have the local information, the texture, the trees, the asphalt, everything. These are going into different discriminator networks. And because they have different tasks, they can kind of specialize. They don't have to be as deep. Here they're translating sketches into images. But the idea being that you have a sum of GAN losses for these for these multiple different discriminators, and basically the generator has to fool all of them. They also do one more thing a little bit similar to the supervised learning term, the sum of absolute valued errors in Isla et al., which is they don't only force the output of the GAN to match the target, in this case the cloud image. Here they're actually matching the discriminator features at multiple points through the network. But we'll get back to that during the questions if it's a little bit abstract. The point is, this is an efficient way of building a discriminator network on large images. So they do that as well. Again, there's code. Again, it's in PyTorch, and it's really available. Okay, so those are a few of our ingredients. We've got our discriminator built with multiple input scales. We've got our UNet architecture, and we've got the extra supervised learning term. So this is kind of a hybrid between a pure GAN and supervised learning with absolute value error term. One more thing they do, that they also take from Isla, which is a bit tricky, is, so normally we talked about in the GAN framework, the idea if you have some noise, which you feed into the generator, and then this produces a fixed sample. And you get diversity in your output samples by diversity in your input noise. And it's important to have diversity because if your generator always outputs the same cloud image from the same meteorological variables, the discriminator will learn to identify that as a fake. Like if you were printing counterfeit money, you wouldn't print them all with the same serial number because it would be a dead giveaway. You need to have variability. And this is a standard approach. What Isla et al. Do, however, and what Schmidt et al. Do in their cloud generation as well is a little bit different. Instead of generating random noise inputs, they don't have any random noise inputs. But what they do is a technique called dropout, where if we look at their architecture, say in our UNet architecture, we have activations of our neural network units at every point in this U-curve, right? And with a certain probability, generally 50%, they just set each activation to 0 during training and when they use the network to test it. So there's randomness in the outputs. Every output of every one of these units at every point in this network has a 50% chance of just dropping out. And this allows them to generate variability in a different way, which they found to be more robust. I think it does open it up to some criticisms, which we'll maybe get into in the discussion phase. So we have one more trick we want to cover before we open up to general discussion. But if anyone has questions, yes. So there's a good question from Eduardo in the Zoom chat. What is the difference between GANs and conditional GANs? I've kind of skipped over this, but let me go back to it, right? It's pretty simple, but in practice it can lead to a lot of complications. So if we just think of the vanilla GANs and conditional GANs framework, right? We're using this objective function from Goodfellow et al., the original GAN paper. We're not using any of these fancy tricks. So if we look at a GAN without any conditioning, we have noise that gets fed in, the generator transforms into fake data, and then the real and fake data get fed into the discriminator. And that's it. We're essentially learning the probability distribution of the real data with our generator. So the generator is going to generate outputs which, if the discriminator is optimal, these generator outputs should converge under some assumptions to the exact same probability distribution as the real data. So we're learning that distribution. Now, what if we don't only have a bunch of data samples X, we have XY pairs, where Y is, for example, meteorological variables like wind speed and surface temperature and so on. And X is the image of the clouds taken by the satellite, or rather the reflectance. So in this case, the architecture changes just a little bit. The discriminator, before, it just took an image of clouds as an input. Now it will also take the meteorological values as an input. The generator, before, only took this noise as an input. Now it will also take the meteorological variables as an input. So basically this Y, and we're estimating the distribution of X given Y, right? So we have these XY pairs. The discriminator is going to see an XY pair. The generator is going to see only the Y and has to generate an X. And then the discriminator always sees a real Y, that is a real set of meteorological variables, and then the X, the reflectance pattern of clouds, is going to be either real or fake. So the generator's task is, given these meteorological variables, generate a cloud pattern consistent with them that will fool the discriminator. And the discriminator's task is, given these meteorological variables, determine whether the cloud pattern is real or if it's a fake generated by the generator. And in terms of architecture, it just means adding the other input variables Y, again in this case the meteorological variables, as inputs into the generator and discriminator. So just as one more input channel. So hopefully this answers the question, but definitely follow up if it's not really clear. Okay, so one more trick, and I think the sheer number of these tricks, and we're not even covering all of them in this paper, really shows you how specialized and how what feats of engineering these networks are. And to their credit, they've shared code, not only for all these papers they draw on, but for the original paper as well. There is code online, and you can download it and you can run it. So it's not like they're keeping their tricks a secret, but to get this working, you really need a lot of tricks. And you have to assume they must have tried more tricks that didn't work. So the last trick, it's a little bit of a funny one, but they're changing the laws. Only need to look at equation 9 here. This is Mao et al., where they create something called a least squares GAN. So if we go back to the original GAN objective functions, right here, yes. So we're maximizing for, we have a discriminator output which we're interpreting as the probability that the data is real as opposed to fake data made from the generator, right? So we're maximizing for the real data that log probability, and we're the generator wants a high output for its data. The discriminator wants a low output for the generator data. Okay, this is a principled approach, and it works, and there's even convergence proofs if you're into that kind of thing. But they do something a little bit different. So I'll tell you what they do in these least squares GANs, and then I'll try to explain why. What they do is, instead of, for the first term, which can kind of still be thought of as a probability but kind of not, the first term, in case the x is really from the data, they want the discriminator to output 1. And they want it to output exactly 1. It's penalized for being too low. It's also penalized for being too high. So typically what you do to build a function, to build a discriminator that's going into a function like this, where you're maximizing log d, d would output some number. You then put it through an exponential function to get something positive and do some additional normalization with a softmax to get it between 0 and 1. And then you'd put it through here. So it's really a probability, and you force it to be between 0 and 1. In the least squares GAN, you don't do this. It's just going to be some number, and you don't generally put constraints on it through the neural network architecture. So it's just some number, and therefore it's going to be close to 1. It shouldn't be too high, it shouldn't be too low. Likewise, if the data is fake, they want it to be close to 0. So they don't want it to be too high, too low. They just always want it to be close to 0. And then the generator wants, for the fake data, the output of the discriminator to be 1. So it's a different scenario, right? It's not a probability. D can be negative. It can be bigger than 1. But it is like a probability in the sense that the discriminator is trying to get it toward 1 for real data, 0 for fake data, and the generator is trained to get it to 1 for fake data. So the same adversarial task. So why do we want to do this? What was wrong with this perfectly principled probabilistic interpretation? Well, we force the discriminator to have an output between 0 and 1 and interpret it as a probability. Then we add up all these logs because we're multiplying. Well, you can do that. The reason that they prefer this least squares formalization is sort of explained by their figure 1, right? So here's the loss term as a function of the discriminator output. So in the original Goodfellow log of d, what we find is the log is a function which slowly starts to saturate, right? Like, or rather, the sigmoid starts to saturate because the architecture forces the number between 0 and 1. When it's already very close to 1, no matter how you tweak the weights of the neural network, it's not going to change very much, right? Because in order to get it to stay between 0 and 1, you need to put it through a saturating sigmoid function like a softmax. And this means the gradients are going to be very small with respect to your neural network weights when you're already very close to 1 in your D function. Whereas the least squares formalization here is exactly what you'd think from least squares. It's a parabola. So the gradient is not 0 over a large region of D output. So here, when the discriminator is giving output very close to 1, whether it's correct or incorrect, changing the neural network weights won't change it much because this function is pretty flat. And this is basically the input to the sigmoid function. Whereas here we don't use a sigmoid function, we're just doing least squares. We find that it's really not flat anywhere, which really helps you train a lot. If you're in this region of the curve, it's very difficult for the network to learn because the curve is flat. It's trying to move along this tiny, tiny gradient. So it just doesn't train well. So basically, by replacing the saturating sigmoid with the least squares, right? By replacing this D function, which has to be between 0 and 1 because it has a sigmoid at the end, with this, our equation 9 here, with this formalization here, where D can be anything, and we just force it to be close to 0 or 1 using the objective function, we have gradients which are non-zero in a much larger region, and we're much more able to converge with our algorithm. So this is why they do this. This is one more trick. There are other tricks which are just too complicated to get into in this session, but they're in the paper if you want to read about them. There's also a question from the chat. This is from Marcel, but passed on a question from the YouTube chat from Alvaro Cantero, who's a member of the computational neuroengineering group in Munich, where Marcel and I are both alumni, actually. He's asking about low frequency information. If you use the L1 supervised loss term over the whole image, why not also over hierarchical intermediate scale patches? Well, that's a good question. If you didn't want to load the whole image in memory, you could do that. I mean, they are loading the whole image in memory, and the L1 loss basically sums up the absolute errors for every single pixel in the image. I think it only makes sense to go to smaller image patches if you're taking into account multiple pixels at once and their relation to each other. So for the L1 and L2 losses, I don't think it helps to go to smaller patches unless you can't fit things in memory on your GPU. On the other hand, there are some fancier techniques which also force the L1 or L2 loss of the activations of intermediate layers of the discriminator network to be the same for real and fake data. This is done in, I believe, Wang et al., and you guys can read up on that more if you like. It's a pretty interesting technique. Okay, so these are all our tricks, and they put it all together. And this is what they get. They're able to make these cloud reflectance patterns. I'm still waiting for someone to explain what a reflectance pattern is as opposed to just a satellite image, if it takes into account the angle the satellite's pointing at the cloud or the location of the sun or something. But they're able to make these really nice realistic images, and I think it's very easy to imagine how this can be useful for downstream applications. So if I'd like to then model rainfall or radiation balance or local heating due to that radiation balance and its effect on the model, this could be really interesting. So why do this in general? Why we want sharp images of clouds? It's intuitively appealing. The reasons they give for it in the paper I think are a little vague, but I think sort of compelling. They say one could consider working in supervised learning. This is like a pure L1 or L2 supervised learning, just trying to make the pixels match. Given the chaotic nature of climate, we need not a point estimate of the potential cloud distribution on Earth, but rather an ensemble of likely scenarios given initial conditions. I mean, that makes sense. Why exactly we want this is a little bit less clear. I guess it really depends on the downstream application and what you want to do with it besides just making pretty pictures. So, and I think we have now, thanks to Eduardo, an actual explanation of what is the reflectance. The energy reflected back to the satellite in a particular frequency band by the cloud or by the surface. I see. So it's actually just the energy. So it's proportional to photon count and probably proportional to pixel values in some range. Okay, so it doesn't take into account the angle of the sun or any of this. I mean, if you look on the Aqua and Terra website, and they actually have a lot of detail explaining their models, they do seem to have these analysis products available where they'll tell you the distribution of different cloud crystals, and I guess this has something to do with the orientation of the satellite, Earth, and Sun. But okay, this is much more like the pixel values. The scatter angle is an input variable. So what is the scatter angle there? All right. Chris, you have a question as well.
Yes, there's uncertainty. There's no cloud expert, right? I mean, and me neither. So, and I have no idea what this angle is. Probably just the angle of something of the satellite looking at Earth, something like that, probably. And then you get the errors different, and you have to kind of interpolate stuff, and that comes into play. But is there someone saying something in the chat? No. Okay.
Yes. Eduardo.
Okay. Eduardo checked it. Okay, good.
So it's the angle between the line of sight of the satellite and the vertical, essentially the normal vector of the Earth, I suppose. Okay. So it's that information is provided, which I think makes a lot of sense. Okay, great. Because you would expect a different reflectance pattern if you're looking straight down, or if you're looking at it from an angle, and then of course the interestingly, I don't know if they provided the time of day. You'd think that would be useful information as well. It may be that the satellite is in some kind of synchronous orbit, so it doesn't matter. I don't know. Oh, but I'm sorry, Chris, you had something else to add?
Yes. So, clouds are important for the climate system for a lot of things. So it's more than here what we see in satellites and that stuff. And the problem is that you have always, like, the cloud calculation takes a lot of computational time, and there are a lot of people trying to improve clouds and models and so on. And this comes into play here with that stuff. So producing clouds out of temperature, wind, humidity, and that stuff, that's basically what a numerical model does. So it's kind of the way of this idea of training physics into the AI, which then makes a decision to say it's a cloud or not a cloud. And then you can get rid of parameterization or convective calculations and that stuff, because on these global models, you don't have, you basically don't have the convection schemes calculated by the model, but rather than just some statistics saying there's now a cloud or something happening, and on a vertical scale or something like that, for the wind in the vertical, for example, and that stuff. So that's what comes here into play with that stuff. And I found it, so you made a great job explaining everything, because I had also a problem with all these tricks. And I just want to add something here to the GAN problem. And I think that's why they did all these tricks, because when I first read about these GANs, I was fascinated by it. I mean, it's a brilliant idea. It makes unique results. The problem is it makes fake data. And it makes so good fake data that you can't kind of distinguish between real and fake, right? However, let's stay with the cloud. If you produce a cloud, it's kind of a realistic picture, but it's not the realistic picture, right? And that's kind of an important thing here. And I'm pretty sure when they started with the GAN, they saw that the pictures looked real, but they weren't the same as the satellite image. And then they started to get rid of the noise thing and went to the dropout thing, and so on and so on. So that in the end, and they added this supervised model next to it to kind of make a classification deep neural network next to it, to kind of say, oh, now you're real or you're not real, and kind of give it a real perspective there. And I think that's why they came up with all these tricks, to have in the end the clouds not just being realistic in terms of statistics or the distribution behind it, which would be okay, but now they get kind of something really close to the reality. And that's, I think, why they made all these tricks. And I also didn't get everything there.
I mean, but do you think it's bad to have something which generates convincing fake data? You think it makes you overconfident in the results when really there's is kind of fundamental quantitative differences? Is that what you're saying?
Yeah, basically, what do you do with fake data, right? I mean, you can use that fake data to produce a large data set to test again things, right? If you, let's say, you make a lot of faces, and then you want to test things on what is the distance of the nose and the ear or something, you can do that with a large data set then. But or you can do, I don't know, but on the climates or on the weather scale, we are on the weather scale here. So what do you do with a picture which is kind of realistic, but it's not the real picture, right? So what do you do with that? And
yeah, it's a good question. So I mean, so a general problem with GAN research. Oh man, we've got a lot of questions. I'll be quick. A general question with GAN research is, how do you evaluate the samples? Because unlike a lot of other methods, they don't give you probabilities you can plug your real data into. They just give you sample output. So it's very difficult to estimate what's a good sample, what's not. You know, if you look at some of these papers, they're actually going on Amazon Mechanical Turk and paying people, you know, a few cents a click to tell which image looks more realistic and seeing how often they can fool real people. And okay, that's nice, but that's not the point. That's not really science. It's like, okay, we can make pretty pictures to fool people. But in this case, we actually do have good measures. So one thing I would love to see here is, well, okay, obviously you can't really do this with 3 channels, but if you were to get a lot more outputs, a lot more different radiation bands, then you could actually calculate the energy balance. And then I would like to know, how accurate is this energy balance compared to, say, a parameterization-based approach, or even an expensive, high-resolution approach run for a short number of steps. So can we actually get a good parameterization? And if I use this as a parameterization for my climate model, and then I feed back the radiative balance to kind of, okay, now there's going to be warming here but not there because of the cloud patterns, well, what would that do to the long-term stability of the model? Would this make a reasonable climate model, or would it be nonsense? So it would be interesting to see how this could be used to evaluate these samples. Okay, lots of questions here. Tobias, Weigel, you want to ask something?
Yes, so when Christopher was explaining and discussing here, I wondered, and I put this, at the very least we could use this to interpolate clouds to really high resolution, right? So meters or whatever. But then it got me thinking, and of course also do this not just as an image seen from top, which in this case, this example is, but also the 3D structure of the cloud, right, with multiple that. But then we are at an interpolation problem, and possibly this again is possibly not the most efficient way to work on an interpolation problem. So I was just wondering whether well, if the answer is something like yes, you could use this to interpolate cloud data to high resolutions, but then again it's possible, but it's not the best tool to do this. You don't need a GAN. You could also use something that is less complex to train and to optimize and to make all these tricks with.
So I think maybe another expert could tell a little more about this than me, but what I can tell you is, all right, so as far as interpolation and so the interesting thing about what they're doing here is they're not exactly interpolating, because they're not actually taking the clouds as input. They're just taking the meteorological variables, and they're creating new clouds from nothing, essentially. Or at least not from information about clouds, just the overall humidity, the overall temperature, the overall wind speed, and so on. But you can use GANs to do super resolution. So you take an image of of one resolution and you output an image of a higher resolution. They have been used to do this. I believe it may be cited in the Big Goodfellow tutorial. I'm not sure.
There are actually a lot of papers on SR GANs. So, and they're battling a lot on making high resolution pictures. So I would say yes, Tobias, that is a way of interpolating. If it's the most efficient, I don't know, because training these GANs is something complicated, but.
Yep, exactly. So it's a very heavy hammer to put that nail in.
Yes, so but that makes kind of this, what they did here in this paper so interesting. So here they can do more, and that's what David said. They can do more than just doing high resolve pictures. They make kind of a classical prediction from different variables to another variable, but in a very precise way in the end, because these GANs have the problem that very, very simple, the question of reproducibility in science, right? If you push the button and it makes a picture, and you push the button a second time and it produces another picture, this is something kind of difficult in producing now clouds or something like that. And they wanted to get rid of that. And and that's why they kind of took in the second L1 layer here, and so I think it's really, really cool, actually.
If I also can quickly chime in on the super resolution, if we do get back to the Wang et al. Paper once more, they actually have a generative GAN that does image-to-image translation, and it adds, in principle, multiple steps for getting higher resolutions at the same time. I think that's figure 3, if we're still on the same figure. Exactly this one.
Figure 3?
Yeah, exactly. So there you have the generative network G1, which is the brown box, which produces a prediction at a low resolution. That's the right-hand side of the brown box. You see the little image. And then on top of that, you stack that second generative network that takes the output of the first one as the conditional variable, this G2, that's the black one. And it produces a higher resolution image. And as they say in the text, which you can just see in David's screen at the bottom left, you could in principle have a third one, a G3 and a G4 and so on, that just doubles the resolution with each network.
And if I understand correctly, the idea is you train G1 and then you sort of fix it when training G2?
I think they say that the cascade makes it easier to train, but I think they do train them in parallel. I'm not entirely sure right now.
But the point is you get a good initialization by looking at things on low resolution, and then you have a good start.
Yes, it does match the idea of the multi-resolution discriminator that you talked before, that it helps it give a more global perspective, because it runs, I think, similar architectures on the low and the high resolution. And then the low resolution is closer in lower layers to getting a good idea of what the full picture is.
Yeah, I feel like I've seen this idea of increasing the resolution as you train the generator in other papers on GANs.
I think there's other papers on hierarchical GANs.
So we have another question from another neuroengineering alumnus. Purnima Ramesh is here as well. What do you have to ask?
Hi, no, I don't have a question. I just wanted to add to the previous discussion about like having GANs that are that sequentially get better at producing super resolution images. There is some work where you start off with a GAN that produces low resolution images, and then you essentially update your generator and discriminator architecture as training progresses. This is a paper from Han et al. In IEEE from last year. And this is something that they do for like MRI images, but this is also like another way of getting super resolution images. I just wanted to point that out.
Well, thanks. Yeah, let's find that paper and put that in the description on YouTube later. Yeah. Okay. I have a question, and I want to encourage people to draw attention to what they don't understand. And leading by example, I will admit I have no idea what's going on in Figure 4 of this paper. We're supposed to be looking at discrete Fourier transforms of the images. So this is one of the ways they want to check. This is generally a good thing to do. Take something your network wasn't trained to do and see if it does it anyway. That's a good hint that it's getting kind of realistic samples overall. So let's look at the frequency spectrum of the images and see if they're correct. Well, okay, we have on the left the images, real data top, and the fake data made by the generator bottom. Then on the right, we have histograms of amplitudes of the 2D frequency components, but what the heck are we looking at in the middle? Does anyone know what this is? You should be able to read the image, the caption. It didn't help me much.
Could this be the real versus the imaginary components of the coefficients for the different frequencies?
That was my first guess, but then why do the X and Y axis labels have the exact same tick marks as the original images? It seems to be valued in pixels, which would suggest that it is actually they do seem to be black and gray. They could be the amplitudes of the 2D FFT components themselves. Like if I zoom in a little more, I don't know how much resolution is coming across the stream, but you can see it's the exact same size in pixels as the original image, so it could be the 2D Fourier transform. And you've got black, gray, and white. But it doesn't look like a 2D FFT should look to me. Maybe they do some special color mapping to get all that white. I don't know. I guess their code is online, so we can check if there's some graphing function, perhaps. But all right. That's about all I have. Chris, yeah.
Now the microphone's on. Actually, I have also no idea what this is. But never mind. Do you have any idea how hard this is to get it run on a computer?
I do not. I have never tried to run a GAN. I know we have at least two people in our chat, Purnima and Tobias Finn,
okay,
who have some experience with GANs. So I would also love to hear how hard is it really to get these things to work, and what do you think of what they did here, of these tricks, of this whole framework? All right, so Tobias, maybe first from you.
Yeah, I started with GANs, I think 2016. So there was a quite famous paper called Deconvolutional Generative Adversarial Networks. And way back then it was very difficult to train GANs, and I think it is nowadays. It remains quite difficult, but I think that there are some tricks which are not mentioned here or which they don't use here, which had quite some impact in the training of GANs. For example, there's much of theoretical work done in constraining the discriminator and the generator to get smoother loss functions and smoother gradients and so on. And yeah, so actually, I think it is possible now to train GANs very, let's say, yeah, in very general terms, but I think it is still more difficult to train GANs than supervised learning.
Can you say something if you do, let's say we are able to make the GAN running, and then this is the supervised learning model next to it. So to combine these two things, do you think this is kind of a hard thing to do? And do we have to train this whole setup at once? Probably, right? Yeah. So this step kind of after the GAN or next to the GAN, what would you say? It's kind of the same effort to get all these tricks on board?
I mean, for example, there's the so-called spectral normalization, which is nowadays quite used for GANs. So this is in some kind of a special normalization layer for neural networks, which normalizes the weights of the neural networks such that they have roughly an eigenvalue of 1, or such that the maximum eigenvalue is 1, and this help to stabilize the training, and of course there's done work done by, I think, or the most impressive work was done by NVIDIA and Google with their so-called style GAN, where they produced hyperreal or very realistic photos with a resolution of 1024 times 1024 pixels, and it is quite difficult to discriminate these pictures from real pictures. But I think, yeah, it is kind of tricky, but I think it is doable.
But we can't use their work, right? We have to do this whole hyperparameter tuning by ourselves, right? Because of the question.
Yeah, I think yes, because they are specialized in training images or generating images, and I mean, if you want to generate a temperature field or something like this, then of course you can use similar architectures, but of course you have to do your hyperparameter searching for yourself, and I think that they will be quite different, and so and I mean it is so I think the more high dimensional data you want to create, the more difficult is to train again. So I think it would be quite difficult to train again for, let's say, a temperature field of 10,000 times 10,000 pixels or something like this.
Yeah, I mean, in Isola et al., they claim to be trying to create a general framework which will work with many different kinds of image translation tasks. Whether that's really true, I don't know, but that's at least what they're going for.
Yeah. I mean, so this pix-to-pix training is in some kind of supervised learning only. So there's also some follow-up work called cycle GAN, where they trained image-to-image transformation without knowing the exact pairs. So where they have a data set of dogs and a data set of cats, and then they train neural networks to translate from a picture of dogs to a picture of cats without knowing the exact mapping. But
because you mentioned dogs and cats, I feel this session would not be complete if I did not show the case where they trained their pix-to-pix method to translate sketches of cats into actual cats, right? So you give it a hand-drawn sketch of a cat. I don't know if they show the normal version of this. But having done this, they then took someone who basically, they drew by hand. This is sketch filling in the sketches. But having trained this to move sketches of cats into photos of cats, they then put this into essentially a sketch of what to me looks like a loaf of bread with two eyes on it. And I think this image is just too fantastic not to mention. Equally appealing is that it translates a photograph of a bunch of keys and electronic components into a painting of flowers. Yeah. Purnima, did you have comments on the GAN training? And I know you've got quite some experience there as well.
I have to qualify whatever I say by first admitting that the GANs that I've trained have been on quite different kinds of data. I haven't really trained GANs to generate images, but having said that, I agree with almost everything that Tobias said, that there's lots of other ways now to stabilize training and prevent mode collapse. There's actually a lot more, like spectral normalization, for example, is quite nice in handicapping your discriminator, for example. In terms of hyperparameter tuning, again, it varies quite a lot what architecture you would use and what hyperparameters you would choose depending on what problem you're solving. As for the dimensionality of your data set, I think there are also ways to deal with that. For example, some image generating GANs, usually what they do is they first try to produce generate a lower dimensional or a low resolution image, and then scale it up to a more higher resolution one. I can't immediately recall any citations for this, but I do remember some papers where they first get the GAN to generate low resolution images and then scale up the resolution. And this is, so again, like even when you have limited GPU, like limited computational power, basically you can still manage to train the GAN even on quite high dimensional data sets. Of course, with all of these tricks, there are just more and more hyperparameters to tune. So the actual training time might not be so hard, but I think the real effort of training a GAN goes into just like hand tuning all of these sorts of like hidden hyperparameters and it's not always clear from reading the GAN papers.
Thanks.
Thank you.
Tobias, you had more to say on that topic too?
Yeah, because I have to admit that I'm a little bit concerned about the usage of Dropout because they claim that they get a diverse, different cloud fields out of it, but I don't know if they really capture the data uncertainty out of it. So if it is by using the Dropout, I don't know if they really capture the distribution. So if they for example get as output that this pixel has a reflectance uncertainty of plus minus 10 or something like this. So I don't know if it is then really tuned and so if it is really capturing the uncertainty because normally the nice things about GANs is that they reduce the so-called Jensen-Shannon divergence, and so it is in some sense similar to the Kullback-Leibler divergence, and normally normally by using input noise they are able to reproduce the real distribution, or the, let's say, the data distribution, and I don't know if it is possible if one would use only dropout instead of noise.
So I mean, I think it's a very good point. Marcel and I were having some similar discussions earlier in this week. Marcel, I think you're also skeptical of dropout in this aspect, right?
Yeah, I would just point out that they cite again Isola et al. For using the dropout instead of an actual noise source that they would transform from. And Isola et al. Themselves in their paper note, and I'm quoting, "Despite the dropout noise, we observe only minor stochasticity in the output of our nets. Designing conditional GANs that produce highly stochastic output is an important question left open by present work."
Yeah.
So people that introduced the dropout replacement themselves were very unhappy with the variability of the outputs.
Yeah, and they weren't really trying to get it. Maybe they would have liked to have it for these image translation tests, but yeah, I mean, I agree. If it's something that has to be investigated, and no one has convincingly shown that it captures the full variability of these distributions, right? The full range of samples, either in the data in the unconditional case, or in the data conditioned on the other inputs in the conditional case, like here. I don't see any reason why it shouldn't be possible to do this with dropout. If you have the right network architecture, it's still a way of injecting noise, right? Especially if it happens in the early layers of your network, and you have enough of these dropout units. You should have, like, if you have n units with dropout, you should have 2 to the n possible configurations. So this is like a reasonable approximation of Gaussian noise at some point. But whether the network actually learns to use it is a different question. And it does seem like, looking at Isola, they say they tried it with Gaussian inputs for their noise, but then the network just learned to ignore them completely. So I don't know what's to be done there. Yeah.
What does ignore mean?
Well, it means those noise terms are fed into the inputs, which means just like any other inputs, like the meteorological variables or anything, they get multiplied by a matrix and then put through a point-by-point nonlinearity. I think in this case, the hyperbolic tangent, right? So you have your inputs, you multiply them by weights, add biases, do a nonlinearity, but those weights are learned, and those weights can go to 0. So, or they can go to something very small relative to the effect of the biases or relative to the other inputs. So the network can learn to ignore features it doesn't want to pay attention to, which is actually, I think, much more of a feature than a bug, right?
Yeah.
But in order to fool the discriminator, it chose to basically ignore the noise inputs and just come up with something deterministic. And in theory, with enough data, with enough training, that shouldn't work, because it's like printing the same serial number on every one of your fake bills. And the discriminator should realize, oh, when I see exactly this input pattern down to the exact bit, it's got to be fake. But it didn't seem to happen. Now that we're zoomed into these things, I wanted to look at the variability and because Tobias was pointing it out, and do we really get, it looks like we only get variability in the high resolution features, but not the low resolution features of the global aspects. But if I look in space next to the planet, because the satellite is really collecting, I think, presumably it's transmitting bits of space as well. I've got these brightly colored pixels. I don't know what they are. If they were cosmic rays, they'd be all over the sensor, not only on the outside. So I don't know what happened here. I don't know if you can see this on the stream, but it's kind of a funny curiosity. What do GANs make and why?
Oh, wow.
It looks like CCD sensor noise. And we're also beginning to see these checkerboard patterns over Africa. So, not bad, not perfect.
And I've also another concern because they try to so they used actually model data to generate photos, and the model data has also errors on it, and the target images have also errors. And so I don't know if it is really the best way to combine model information or to condition to condition the image information on model information, because it could be that the model sees the cold front 200 kilometers away from its real position, and then the image shows it at the real its real position, but the model has it wrong, and then the GAN has to generate some artificial features.
Well, yeah, that's true. You always have to be careful about errors in your data, but is there anything they could do here?
I don't know.
Yeah, they could use the clouds in the reanalysis data set.
Yeah, probably yes, but then it wouldn't be so high dimension as so yeah.
But that's a very interesting check. On average, it should be something. Now, but the clouds, if you're talking about error 5 or a different reanalysis data set, they have parameterizations. But do they actually have? No, they do have variables. I recall, yes, the total fraction.
Oh, they have definitely cloud cover.
Cloud cover.
Yeah, definitely.
I think they also even have the fraction of moisture in ice crystals and in droplets. I think those are variables you can download from ERA.
Yeah, and you have these satellite products from ERA, because ESA is kind of depending on ESMWF there. So definitely there are products there. And that would be, that's what I always ask myself. And Tobias, you're totally right that there's a lot of sources of uncertainty. And I mean, you have to capture these things, and you can kind of get like numerical biases or something if you kind of force the neural network to kind of learn something which isn't there. So a good first check would be like checking the clouds from this satellite product next to the reanalysis product, and then do this mapping thing. So I have kind of a cross-validation thing. And then you have an amount of the uncertainty between the clouds and the reanalysis product and the satellite. And then you have an idea of, when you reproduce now kind of real satellite pictures with the reanalysis data, what the uncertainty is in there between. So, and you're right, David, there's parameterizations and the clouds and the reanalysis. I mean, nothing is real, right? I mean, nowhere, right? I mean, I'm pretty sure it's pretty close to the variables in the reanalysis product. So let's keep it like that.
Well, any more questions or comments from anyone? Any topic? Just chime in. Oh, there's a comment from the chat from Purnima. With respect to dropout noise, here's a paper that argues that dropout noise translates network parameter uncertainty, that is the uncertainty in the neural network parameters, into generated data uncertainty. Okay, great. So we will post that in the chat as well. Here it is on the stream for a second. Okay. Kingma and Welling, some of the most ubiquitous names in machine learning. There's a very good chance that they have something interesting to say in this paper. Okay. And Tobias is pointing out another paper relating dropout to Bayesian variational inference. Okay. Yeah, it really shows how all these different fields of machine learning can really relate to each other. We started with GANs, we've done supervised learning, we've done UNEDs, convolutional networks, different loss functions. We are now getting into Bayesian inference and uncertainty representation. Chris, you still have your hand up? Is there anything else you want to add?
Sorry, no.
Okay. Any other comments? Any other questions before we wrap up?
David?
Yes.
I have a sort of a general question. So you mentioned this blurring effect in supervised learning, so that the pictures come out blurred without detail.
Yes.
Because they cause just a reversion to the mean, I guess.
Yeah, if you're using a sum of square errors loss, it's a regression to the mean. Or it's basically, yeah, you're trying to get the average outcome correct. With the sum of absolute value errors, I believe it'll tend to be more like getting the right median. But again, for each pixel independently, so not taking into account the fact that nearby pixels should be consistent with each other. There's no concept of moving the storm east or west. It's all on a pixel by pixel basis.
Yeah. So my question, as I said, is it's sort of general. All these supervised learning methods produce, or the question should be, do these supervised learning methods always produce this blurring or tend to produce this blurring? And are the GANs the only way to avoid it?
No, in fact, they're not the only way. So one of the best things you can do, and I think this is preferable over every other method if you can do it, is to simply write down a probability distribution on the outputs, which is controlled by a neural network, right? So the neural network takes the inputs, it processes them a bunch, and then it outputs a probability distribution. Now you can think of the sum of square errors as outputting a probability distribution. It's just a Gaussian. It's a Gaussian with the mean, which is the neural network output, and then it's a diagonal variance, same variance for every dimension. So it's basically the sum of square errors corresponds to that probability distribution of outputs. But okay, what about the absolute value of errors like they used here? Well, that's just, I believe it's a Laplace distribution. It's just, instead of the e to the negative delta x squared, you get e to the negative absolute value delta x. Okay, but you can go much further. For example, the neural network could output a Gaussian with non-diagonal covariance, which is to say a Gaussian which has got rotated axes so that the multiple pixels relation to each other matters. Or you can go further and further beyond this, and then you start to get into the realm of normalizing flows and autoregressive models. So I think this would be an excellent topic for a future machine learning seminar, is a case where people, I don't know if we'll find an earth science application, but we might just, but where they come up with an output, a trained neural network, which not only generates samples, but can also calculate the log probability of any given input. So instead of saying, I'm just going to spit out samples of clouds, spit out possible cloud covers, the neural network, given those meteorological values, should be able to estimate the log probability for any possible cloud cover image. So you should be able to show it a picture of the real clouds and it should give a high value. You should show it a picture of Mickey Mouse's face projected onto the earth and it should give a low value for that. And it should capture all these aspects of it. But in terms of a function, a probability function on cloud images, which you can take derivatives of, which you can evaluate for whatever you like. If you can do that, then you can very often fit non-blurry distributions which capture all these high-dimensional features, which don't only produce samples, which don't require you to train two adversarial neural networks at once. So this can be a much more powerful approach, but it's a very new approach and it has limitations, and no one has gotten it to work for such big images as we've seen here. So this is it's a question, and I think a question a lot of people at the intersection of earth science and machine learning are thinking about. What is the right way of representing these uncertainties, these probability distributions on images? Do you want to use a GAN? Do you want to use one of these normalizing flow methods, which I think we'll cover in the future? Do you want to use a variational autoencoder, which is another approach we may cover in the future? Or is this some new thing that we haven't even invented yet? So this is, in principle, is possible, but for this resolution and this size of images, I think GANs are the only methods which have really produced consistent results so far.
Okay.
Tobias, yeah.
Yeah, I mean, there's also the trick to turn your problem into a classification problem. So to switch from a regression problem to a classification problem to binarize your targets. So this was done with these radar images, and I think this is also in some sense a way to get a quite sharp image out of it.
I'm not sure I understand. You have an image-to-image translation task, and you want to change this into a classification task. You mean just what GANs? You mean the discriminator that GANs use?
Yeah. So this was done in the radar forecasting paper. So they actually wanted to match the reflectivity, and this would be normally a regression problem. And then they binarized their reflectivity. So they binarized, for example, from 10 dBz to 11 dBz, from 11 dBz.
Which paper are you talking about?
About the radar paper 2 weeks ago.
You mean the MetNet?
Yeah.
Oh, they were predicting precipitation.
Yeah. But I mean, so it is so. Predicting precipitation is also a regression problem, like this one.
Oh yeah. I see what you're saying. So basically, yeah, they only care about getting the right value for each pixel. And in their case, they did some fancy, complicated stuff, but I don't think they would claim to produce realistic precipitation patterns. They even mentioned this, I think, and they have exactly the same issue with blurring that that supervised learning tends to have.
Yes, of course, but if they have used L2 or L1 as cost function, then I think they would have a greater problem with blurred images.
Yeah, I think you're right, and I think right. So it's another, yeah. In the end, though, you need some way of taking into account multiple pixels at the same time and their relation to each other.
Yes, of course.
In not only in the input but in the output, and this is something that GANs do, but that MetNet does not do, at least not yet. Yeah,
it's true.
But I mean, yeah, someone could take the whole MetNet architecture and then just stick a generator network on the end of it, especially because they have big input patches, but their output patches are pretty small. So maybe they could generate realistic precipitation patterns that way. Yeah. If somebody has, 64 or 256 tensor cores lying around, they want to pay $20,000 to do this experiment. Okay.
Sure.
Huh?
Sure, we should do that.
Yeah. Any other questions or comments? Okay, then thanks everyone for participating. This was a really nice session. I think we didn't go over too long this time. I definitely learned a lot. And if anyone has a topic, if they'd like to present a whole paper, if they'd like to present on their own work or some topic dear to their heart for 5 minutes, just drop us an email and we will do our next session in 2 weeks. Thanks.
Thanks, David.
Thank you. Thank you very much.
Thank you.
Bye. Bye.
Bye. Thank you.
Bye.